Hello everyone. We'll be solving a very short problem on particle kinematics, and in this problem we will be looking at a particle that has a variable acceleration. It's similar to one of the other problems that we have solved. There is nothing special in this problem. It's just a matter of the integration being performed carefully. Okay. All right. So here is the problem. Okay. So problem. So in this problem, I have a ramp as I'm drawing right here. Okay, there's a particle that is traveling starting from the beginning of the ramp. Okay, so the particle is sitting right here. Okay, at this point on the ramp, the particle has a certain initial velocity that is given to it. Okay, let's say that this velocity is some v naught. Okay, and this velocity is along the direction of the ramp. And let me call this position as position 1. Okay, then what happens is that as the particle travels down the ramp, the particle faces an acceleration which is given in the following form. Okay, so at some point, at any point along the ramp, the acceleration of the particle is given as a is equal to c1 minus c2 times v. Okay, this essentially tells you that the acceleration of the particle is a function of the velocity of the particle. So which means that in essence, this is something that we discussed sometime in one of our online meetings. We said that, okay, if the acceleration contains a velocity, then this means that there is some kind of a drag force that is acting on the particle, and it's trying to reduce its overall velocity. Okay, the particle comes to rest at position 2. Okay, so here is position 2, which means that when I look at the particle, I guess I was using a different color for the particle. Okay, so as the particle comes here, it goes to rest, and so the velocity of the particle at this particular position is going to be 0. Okay, so velocity at position 2 is equal to 0. So this is essentially velocity at position 1. Okay, and what are we supposed to find out? We are supposed to find out the total distance traveled from point 1 to point 2. Okay, so here is the problem. So particle travels down the ramp. Okay, starting with an initial velocity v naught. Okay, particle faces an acceleration in the direction shown. Okay, so the particle has an acceleration that is given as a function of velocity and this is a is c1 minus c2 times v, where c1 and c2 are some constants. Okay, so where c1 and c2 are some constants. Okay, what are we supposed to find? Okay, so find the distance traveled by the particle before it comes to rest. Okay, so the maximum distance traveled when the particle comes to rest, okay, and the time taken to travel this distance. Okay, time taken to travel this distance. Alright, so this is a problem in rectilinear kinematics. As you can very well see, the particle is traveling along a straight line trajectory. Okay, which means that we start off by making use of rectilinear equations. Okay, so the first thing is you notice from the problem that this is rectilinear kinematics. Okay, that's quite evident from the problem itself. Okay, so in terms of the solution, here is how I start this particular problem. Okay, so solution. We notice that this is rectilinear kinematics. Rectilinear motion, which implies that the equations that I have that hold true are the following, which means that the equations are the following. Okay, A is dv by dt, then I have v is ds by dt, and then thirdly I have A is equal to v dv by ds. Okay, these equations that you have written here, 1, 2 and 3, these are valid for any type of a rectilinear motion. Okay, so these are valid for any type of rectilinear motion. All right. Then what are the things that are given in the problem? So given, we know that the velocity at position 1 is v naught. Okay, then I can say that, okay, position 1 is the reference position, so perhaps the position at 1 is 0. Okay, then I can say that s1 is equal to 0, so this is the reference position. Okay, then I can also say that t naught is equal to 0, this is the start time. Okay, so this is the first thing that is given to us. Then I can also see from the problem that, okay, when it comes to the position 2, the particle comes to rest. Okay, particle comes to rest at position 2. At position 2, which means that v2 is equal to 0. t2 is the time taken to go from position 1 to position 2, so that's t max essentially, and then s2, I'm going to call it as s max. Okay, where s2 is the maximum length, maximum distance traveled along the ramp before particle comes to rest. Okay, and between positions 1 and 2, we also have that the acceleration is known to us. So between positions 1 and 2, the acceleration of the particle is always c1 minus c2 times v. Okay, so these are the things that are given to us. We need to find the time taken to go from position 1 to 2. We also need to find the distance traveled. Okay, so let me first tackle what to do with what we have. So we notice that acceleration is a function of velocity. Okay, so notice that acceleration is a function of velocity. Okay, so that's the key statement in this particular problem, which means that it depends upon now based on that particular fact, it depends on how you handle the rectilinear motion equations. Okay, so I'm going to start off with the equation where I relate velocity, acceleration and time. Okay, so I'm going to start off with equation number 1. Okay, so from 1, okay, so from equation 1, I have A is equal to dv by dt, but then A is A of v, right, which means that A of v is equal to dv by dt, which means when I cross multiply quantities, then since acceleration is a function of velocity, I have to bring it to the denominator on the term containing dv, and I bring dt to the other side. Okay, so this tells me that dt is equal to dv by a of v. Okay, which means that I can now integrate this. Okay, so I can integrate this from some time t1, which is the same as what I said as t naught. Okay, so this is the time at location 1 if you want. Okay, so maybe let's call this as t naught just to be consistent with what we have. So this is t naught, and then at time t2 I'm going to call that time as t max, the time taken to go from position 1 to position 2. Okay, this integral is going to be going from velocity at position 1 all the way to velocity at position 2. Velocity to position 1 is the same as the initial velocity of the problem. Okay, and so if I do the integration, then I have the following. Okay, so t max minus t naught, this is going to be the integral from v naught to v2, which we called as v max, which is essentially, I guess, the velocity at the maximum distance traveled. So I guess v max is not a good idea to write out here. So v2, which is equal to 0, okay, which is the velocity when the particle has traveled the maximum distance. Okay, and then if I do the substitutions, this is going to be dv divided by acceleration as a function of velocity, so that's c1 minus c2v. Okay, now I'm going to take a couple of shortcuts. Essentially, when I come across complicated integrals, you got to realize that this is a dynamics class, this is an engineering class. I'm not really interested in finding out how to find the integrals, because I think I know how to do it, and I'm assuming that you also know how to do it, right? So which means that I'm going to make use of certain shortcuts. Maybe you can use Wolfram Alpha, that's one good resource for integrals. Okay, so Wolfram Alpha, okay, can simplify integrals. And based on using Wolfram Alpha, I find out that after I simplify my integral, I end up with the following. Okay, so after integration, okay, here is what I end up with, and this is just solely for the benefit of time. We can always do the integration of these by means of substitution. It's fairly straightforward to do it, but here is essentially what I get. Okay, so t max minus t naught, okay, this is equal to, I'm not going to substitute for the velocity yet, but here is what I will end up getting. So this is going to be 1 by c2 times logarithm of c1 minus c2v between the limits v0 and v2. Okay, and then if I do, and this has a negative sign as well, I forgot about that, sorry about that. Then I know that t0 is equal to 0, so I can get rid of that particular factor. Then I also know that v2 is equal to 0, which means that if I do the substitution for the velocity substitution, and then if I go ahead and calculate t max, then I end up getting t max is equal to the following. Okay, so this is going to be after all the simplifications are done. So here is what I end up getting. Please make sure that you know how to do these simplifications. So after some simplifications, okay, so please know how to do this. I'm not going to go through the details of these things. Okay, so I end up getting 1 by c2 times logarithm of the following. Okay, so c1 minus c2 v0 divided by c1, where I have used the fact that log a minus log b is equal to log a divided by b. Okay, so this is one of the answers that we were expecting from this particular problem. Suppose we were to find the time at any point as a function of velocity. I just want to maybe very briefly do that. Okay, so suppose we need to express t as a function of velocity. What do? Then we go through the same steps. And then write the integral as the following. Okay, so we write the integral as sum t naught, which is 0 to some t dt, and this is going to be v naught to some v. We are not going to actually substitute for v2, which is 0 in this case. Okay, so this is going to be dv divided by c1 minus c2v. Okay, which will tell you that t is equal to t naught minus 1 by c2. Okay, or you can write it as plus 1 by c2 after the simplifications, logarithm of the following ratio, c1 minus c2 v naught divided by c1 minus c2 v. Okay, this is a more general equation. Okay, so this is a general equation. Okay, something to keep in mind. Alright, so I found out one of the things that I wanted to do in this problem, and you see this is fairly straightforward. There is mostly nothing to think of here. The only thing is you realize that okay, acceleration is not a constant, it's a function of velocity. So you make use of the requisite equations from rectilinear motion. Okay, then I go to the next part of the problem. The next part of the problem is I also need to find the position at location 2. Okay, so here is what I do next. Okay, so let me call this as part 2. So obtain position as a function of velocity. This is going to be a general expression. Okay, here is how you do it. You know that acceleration is a function of velocity. Okay, so we know acceleration is a function of velocity, so that's c1 minus c2 v, which means that use the equation that relates acceleration, velocity and position. Use the rectilinear equation that relates acceleration, velocity and position. Okay, because I need position as a function of velocity, and this is of course a general expression that I'm looking for. And then when I get a general expression, which is typically how I solve problems, I can always substitute for the actual values themselves. Okay, so the rectilinear equation that relates a, v and s is a is equal to v dv by ds, which means that a of v is equal to v dv by ds. Okay, and so if I do the substitution, then this is going to be c1 minus c2 v. Okay, this is equal to v dv divided by ds, and then do the cross multiplication carefully. The left hand side is a function of velocity, and so you attach it with the terms that contain the velocity on the right hand side. So this tells me that ds is equal to v divided by c1 minus c2 v dv. Then I do the integration. I go from some s naught, which is the same as what I said of s1. I'm sorry, this is s1 is equal to 0. I go to some arbitrary position s. Okay, and then likewise I start from v naught. I go to some arbitrary velocity v, again skipping the details of the integrations. Okay, you can use Wolfram. Okay, for these kinds of details, we are not interested in that. So from this I end up getting the following. Okay, so this tells me that S minus S naught on the left hand side is equal to 1 by C2 square times C1 logarithm of C1 minus C2 times V plus C2 times V between the limits V0 and V. Okay, or if I do the substitution and then I see, okay, I end up getting with S equals S0 plus 1 by C2 square. And if I go ahead and do other things in this problem, so this is going to be C2 times V minus V0, and then I'm going to have a C1 times logarithm of the following quantity or the following ratio, C1 minus C2V divided by C1 minus C2 V0. Okay, and of course if I want to find the position at the location where the velocity is 0, okay, so to obtain S is equal to S max at location 2, all you do is substitute V is equal to 0 at that location. Because why is that? You are told that the velocity or the particle comes to rest at location 2. Okay, so I guess I'm going to skip the details of that step because that is just a basic substitution, but here are the details of the problem as such. And the only thing that you got to keep in mind is that, okay, acceleration is not a constant. Because acceleration is not a constant, I have to go through all the integration steps carefully. Okay, so note that because acceleration is not a constant, we have to go through all the integration steps carefully. Okay, that's something that you want to make sure. Since acceleration is not a constant, you have to start from the first principles. What are the equations of rectilinear motion? Once you know the equations, then you do the substitutions and so on. So please do not blindly use the constant acceleration equations. You have to be able to derive the accelerations or the velocities and the positions given acceleration as a function of some particular quantity. All right, thank you very much, and I hope all of you are staying safe. Bye bye.